Welcome back to chapter 13. This chapter is the beginning of our next unit, which is about probability. So in this chapter, we are going to get a bit of definitions, and we'll see some probability formulas that you've probably seen before, and it won't be a ton of new stuff, but there will be some new stuff in here, um, and some specifications on some old stuff. So we've been dealing with random phenomena. Um, and as we saw a couple chapters ago, random phenomena is not a haphazard thing. It's a situation where we know what could happen. We just don't know what's going to happen on any specific time. Like when we roll dice, just like a regular six-sided cube, 1 through 6. We know that we're going to get a 1, 2, 3, 4, 5, or 6. We know likelihoods of each of those. We just don't know what's going to happen on that next roll. That's what is called random. Um, and so each occasion that we observe, that is called a trial. So each time we roll the dice, that's a trial. For each trial, the value of the random phenomena is the outcome. So what actually shows up is the outcome. When we flip coins, the outcome is a head or a tail. And so it's what could possibly happen. When we combine outcomes, the resulting combination is an event. So rolling dice, it could be the event that we get a 2. It could be the event that we get a 2 or a 5. So that's two outcomes being combined. It could be the event that it's an even number. That would be 3 outcomes that could be combined. So that's the difference between an event and an outcome. An outcome are each of the individual things that could happen. An event could possibly group a few of those things into that successful thing. And then the collection of all possible outcomes is called the sample space. And so when we deal with sample space, it's usually a capital S. And if we had just a 6-sided dice, it could be a 1, 2, 3, 4, 5, or 6. We put it in like a roster notation using the squiggly brackets. If we were flipping coins, 2 coins, or 1 coin, sorry, with 2 options, the sample space could be a head or a tail. And so we could just list it out. If we were flipping 2 coins, we could have head head, head tail, tail head, or tail tail. That would be the possible things that could come from flipping 2 coins. So one of the things that we've seen either this year or even before is the law of large numbers. And what the law of large numbers talks about is when we do things repeatedly. But first, when we think about things, it's nice if they're independent. That makes it easier. It makes a lot of calculations easier. It's not necessary, but a lot of things that we'll do will have that independence as an assumption to what we will do. So what independence means is that the outcome of one trial doesn't change the outcome of another. So here we have an example. The coin flips are independent. You could flip 3 heads in a row. The probability of flipping a heads on the 4th flip is still 50-50. It's 1/2. Dice, when you roll dice, the dice don't depend on the previous rolls. Every roll is brand new. That's independent. That's the basic idea. We'll see an equation type definition in just a minute. But the idea is that one outcome does not affect the next. And so the law of large numbers says that the long run frequency of repeated independent events gets closer and closer to a single value. And that's what we call the probability. So when we roll dice, rolling a 2, we know that that's going to be about 1/6 of the time we roll a 2. Well, if I roll a 2 6 times, that doesn't mean I'm going to get one once. But what the law of large numbers says is that as I roll the dice more and more and more and more and more, the probability of getting a 6 gets closer and closer to that 1/6 thing. So it might be rolling it 6,000 times, I'll get a 6 about 1,000 of them. I don't know in what order that happened, but about 1/6 of the time that I roll it, I'll get a 2. And because it's based on repeated events, it's called empirical probability. Sometimes, especially for smaller numbers, called experimental probabilities with a small number of trials. But it's the repeated observation gives it that name, empirical probability. And so then we have the law of averages, which is not a thing. Sometimes it's also called the law of small numbers. And that's the idea that, I'm due. I'm due for a win. The dice have been rolled and I haven't gotten a 6 in a while. It's due. No. Eventually, yes, you will get a 6, but not necessarily this next roll. Maybe. But there's nothing saying it's going to be at that or not going to be that. If we roll it a lot of times, yeah, those 6s will average out. But in general, we don't know. Like, you're not due a certain outcome. When we model probability, a lot of times we look at what's called theoretical probability. And that's what we do with dice. Like, yes, in many, many, many rolls we've had these, and we know that getting a 2 is about 1 out of 6 times. But more than that, we have these dice. They have 6 sides. All sides are equally likely, and a 2 is 1 out of those 6 sides. So it's 1 out of 6. That's theoretical probability. Same thing with heads or tails. It's equal probability of getting a heads and a tails. And so heads, that's 1 out of the 2 possible things in the sample set. So the events are not all equally likely. I know when we're in class, we do a couple different activities, one of which is we flip thumbtacks, which we may have done a few years ago, depending on what classes you were in. Algebra 2 has a thumbtack flipping thing, which I modified from our calculus activity, where it can be points up or point down. Our statistics activity, not calculus. But it could be point up or point down. What's the probability of it being point up? I don't know, but it's probably not 50%. Or instead of rolling dice, we play a game called Pass the Pigs, where we roll pig dice. They're little dice, but they're shaped like pigs, and they land all sorts of weird ways. And the probability is not the same as rolling dice. And so the events are not all equally likely. And here it gives the example of a basketball player has better than a 50-50 chance of making a free throw. So theoretical probability does not always go with just, it's not always possible. We can't just look at the number of outcomes and the number of successes and then divide, because sometimes some successes are more equal than others. So the probability event is the number of outcomes in the event divided by the total number of possible outcomes. So this is the theoretical probability. Specifically, if the number of outcomes all have an equally likely chance of happening. This is how we get that theoretical probability from rolling dice. We have 1, 2 out of 6 possible outcomes. So its probability of getting a 2 is 1/6. We could do this as an experimental or empirical probability. We rolled the dice 6,000 times. 1,000 of the times we got a 2. So that's 1,000 over 6,000. That's the number of outcomes of A that happened divided by the total number of trials. So it's a little bit different, but it's the same basic idea. But this one specifically is the theoretical probability definition. Subjective or personal probability is something that we will talk about. Like you just use it, you say it like, oh, I'm probably going to do this. Yeah, it's sure it's kind of probability, but that's not what we're talking about. So we don't need to worry about that kind of stuff. So first 3 rules of working with probability: make a picture, make a picture, make a picture. Just like with data, making a picture is huge. It can help us to organize our thoughts. On the AP test, that can actually help get you points. Um, so always make a picture. There's a couple different types of pictures that you can make with probability that are useful. Sometimes a Venn diagram is useful, and we'll see that in just a minute. Um, Sometimes a tree diagram is useful when dealing with probability. It can help get the different probabilities, and we'll see those as well. So most common type of picture is a Venn diagram, it says. I know personally, I have never really liked Venn diagrams in the English sense where we're comparing, contrasting stuff, but um, in statistics, it can be hugely useful because you can see the probability of the overlapping part and the probability of the non-overlapping parts, and um, it makes sections that are what are called mutually exclusive, which we can do things like add together and deal with, and we're going to see that in just a second too. So before we get there, we have some requirements for probability, and these are not a definition of probability, but it's a like kind of properties of probability. So first, a probability has to be a number between 0 and 1. Um, a probability of 0 means that it will never happen. It is impossible to happen. So if I have a 6-sided dice, it is impossible that I roll a 7 because that's not one of the numbers on my dice. And a 1 is something that will always happen. If I flip a coin, it'll be heads or tails. Like I'm going to get a heads or a tail. Like if either one of those is a success, then I'm going to win. Kind of like a heads I win, tails you lose. Whether it's a head or tail, I win. That's a probability of 1. The probability of everything in the sample space is 1. Um, so that's that. And so the box here kind of represents the sample space. Um, Here we're going to use a box and we're breaking it up a little bit. The complement. Now that's complement with an E, not a complement with an I. That would be when one probability says something nice about another probability. This complement is it's the event that A does not occur. So if I'm looking to roll a 2, the complement is not rolling a 2 or rolling not a 2. And it's denoted that it's like a to the c. The c is not actually an exponent. It's like an index. A lot of times that goes down in a subscript instead of the superscript, but for whatever reason, we look at it in the superscript and it looks like an exponent. If we add the probability of an event plus the probability of its complement, we will get 1 because it's either an event is either in the event or it's in the complement of the event. Those are the only two choices. It can't be in something different. It's one or the other. The addition rule. So if two events are disjoint or mutually exclusive, that means they have nothing in common. Rolling a 2 and rolling a 5. You can either roll a 2 or you can roll a 5. You cannot roll both. And for those of you that said, oh, well, but it could land on its side. First of all, that's not an actual outcome. And secondly, no, it can't, because the 2 and the 5 are on opposite sides of the dice. So um, it's mutually exclusive. It just means that they both cannot happen at the same time. And what's nice about that is we can add those probabilities together. If they are mutually exclusive, you just add them. So the probability of a 2 or a 5 means that we could take the probability of 2 plus the probability of a 5 and add them. So it would be 2 out of 6. The notation here, this guy means or, and that's called a union. A multiplication rule. This one, by the way, means and it's called an intersection. So if the two events are independent, then the probability of A and B will equal the probability of A times the probability of B. This is more than just a multiplication rule. This is that definition of independent that's the equation. Two events are independent if and only if the probability of each one multiplied equals the probability of the overlap, which is this. So it says that it's this provided that they're independent. If this happens, that means that they are independent as well. It's a one or the other thing. It's either independent or not. Now, it cannot be independent and mutually exclusive. Mutually exclusive events have zero overlap. So that doesn't work. You can't multiply the two probabilities together, you get 0. So independent events and mutually exclusive events are not the same thing. They cannot be both. Unless one of the mutually exclusive events has a probability of 0, in which case it's not even really an event. So two independent events, A and B, are not disjoint, provided that the two events have probabilities greater than 0. There we go. Because when we multiply the probability of A times the probability of B, we get this overlap, and mutually exclusive events do not have any overlap. So a lot of what we'll be doing this year, we do have to assume independence, but you don't just want to haphazardly assume independence. You want to really think through it. Like, does one influence the other? Like, what's happening? So if we surveyed households instead of individual people, that would not really be independent, because chances are two people in the same household will have the same beliefs about a number of different things. If you don't stay in the same household for very long. Some notation. So as I mentioned, the U thing, the union, means or, and the intersection means and. So its notation, you do need to be able to recognize both. Or means that one or the other happens, or both. It's an inclusive or. It could be both A and B happen. That's not really a problem if they're mutually exclusive, but they're not always mutually exclusive. And we'll get equations for when they aren't. The and is the overlap. It's when both things happen at the same time. So a lot of times we do have to use the various rules kind of at the same time in the same equations. Um, and sometimes it can be easier to work with the complement of an event, especially if you're trying to find when at least one thing happened or no more than one thing happened. If you're trying to find at least one thing happened, well, the complement of that is nothing happened. It sounds like a lot easier probability to find. And then you can go 1 minus that. Things that can go wrong. Beware of probabilities that don't add up to 1. That's problematic. It means you're missing some events. Don't add probabilities of events if they're not disjoint. We'll find or we'll see an example to this or an equation for this in later chapters. But if they're not disjoint and you add the two probabilities, you've added the overlap twice. And so you can get some pretty weird probabilities that way. Don't multiply probabilities of events if they're not independent. This one is a big one. People always just try to multiply them. But if they're not independent, that does not work. You can't do that. Then don't confuse disjoint and independent. They can't be independent. They are completely separate things. They are actually disjoint from each other. But they're always introduced and talked about in the same lesson because they talk about the same stuff. So don't confuse them. Don't think that both can happen at the same time. So what have we learned? The probability is based on long run relative frequencies. Law of large numbers speaks only of long run behavior. Watch out for misinterpreting that and looking at the law of averages or law of small numbers. We have some basic rules for combining probabilities. We know that probabilities are between 0 and 1. The sum probabilities of all outcomes has to be 1. We know some different rules, the probability assignment, complement, the addition rule for disjoint events, multiplication rule for independent events. And then for even the most simple problem, always show work. This is a tip for the AP test. And I know a lot of you are kind of seeing that as as we're doing those problems. It's like, oh man, if I would have just showed a step, I would have gotten a lot more points. Even if it's just showing what you're using to multiply by. I mean, the multiplication will probably be done in a calculator, but what are you multiplying? Write it down. A general rule of thumb is if you put it in your calculator, put it on the paper, but not in calculator notation. So, again, this week we're looking at probability. I'll see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.